Hey guys, so today I'm going to be showing you guys how to solve problem number 13 from WeBWorK 4. Basically, this is an equation that deals with a population model, but it's not like our normal ones that we've been looking at, where it normally just has the change of population over time equal to a constant, a small constant, times the population at that point, times a factor of 1 minus point over another constant k, which we know to be our max population. This is what we've been looking at and what we've been dealing with, but this particular problem is having us account for a minimum population, which this is the number of which the minimum would be divided by the population at that point. Now we can tell which is a max and which is a min because the population is over this certain number and it's 1 minus, so we know that it can't go over that. And then we know it's a minimum because the population factor is in the denominator. So yeah, this is a little bit different from what we've been dealing with, where you're going to see if it's over a certain population point, it's going to crash, but if it's also under a minimum, it will crash as well because it's not able to sustain itself. Now, having taken ecology, I've seen this first part of the equation a lot in a lot of my classes, and this is a type of equation accounting for a minimum that would factor in for an animal like a cougar or a bald eagle. You know, they are apex predators and they are able to sustain themselves on the beings that are around them, but if there are so few of them and they're not able to find a mate, they won't be able to sustain themselves because they're so far and few between. They don't all populate one small area like a deer does. They spread out all over the country. So having that background knowledge, I feel like I'm able to kind of give you guys a little more insight as to what kind of population this would look like. But solving for the actual problem, we first have to find the equilibrium points. So we know that little k is equal to 0.2 and capital K is equal to 10,000. And then the minimum we know is going to be 900. So given these little variables, we're able to kind of put them into the equation. So we come out to have dp dt is equal to 0.2p times 1 minus p over 10,000 times 1 minus 900 over p. Now we have to set this whole equation equal to 0 because that's what we do when we find equilibrium points. We find where exactly that change in time is going to equal 0, meaning it's not going to have a slope. So we have to, what I did in high school a lot of the time was I would break up the equation like this to separate each individual variable. That way I could find, because they're all multiplied into each other, so it's not like they're being added, so they're able to be separated. So 0.2p equals 0, 1 minus p over 10,000 equals 0, and 1 minus 900 over p equals 0. And then we just solve, so we divide out 0.2 and we find that p equals 0. That's one of our equilibrium points. And then we subtract the 1 over from this equation, so we get negative p over 10,000 equals negative 1. And we can get rid of that negative sign on both sides by dividing out by negative 1 in our head. And we multiply the 10,000 over to get p equals 10,000. And then similarly on this side, we also subtract out the 1 and divide by negative 1 to be able to get rid of the signs. So we get 900p equals 1. We multiply the p over, we get 900 equals p. So these are our 3 equilibrium points that we've been able to find. Next is to graph them, because we're making a phase diagram, which is basically like a vertical version of what some of you might have seen in high school, where we're looking at points on certain intervals of the x direction. Now p is going to be our y direction, so we're going to disregard this, but it's similar except it's vertical. So let's put in our points. All right, and then I'm going to just make an equilibrium point just to remind myself that those are horizontal asymptotes. Now we have to find a point on each kind of section. You see that there's 1, 2, 3, 4 sections that are divided out by these 3 equilibrium points. So we're going to find a section that's above 10,000, so that's going to be 10,001. We're going to find 901, and then we're also going to find 1. And -1, actually. So we just plug these basic numbers into the equation found from above up here. So we have 0.2 times 10,000, I keep saying 1, 10,001 times 1 minus 10,001 over 10,000 times 1 minus 900 over 10,001. And then we just plug this into our calculator. What I've done is I was able to put in the entire equation, but putting in x instead of p. Just putting in the whole equation and then having my table set, the independent variable be ask. That way I can just plug in each individual number. That way I don't have to type it in here 100,000 times just to be able to save time. And then you have your numbers right there. So I'm just going to copy and paste these right over after I plugged them into the equation. So this comes out to be negative 0.18202. And I plugged in for 1, and for -1 I made some sign changes. So -1 times 0.2 stays negative, and then we see that 1 minus, originally it said minus, -1 over 10,000 is able to be changed to a positive. And then we also have 1, originally a minus 900 over -1, becomes a 1 plus 900 over +1. So we've gotten our values, and remember in phase diagrams, all we really need to look for is the sign. So we see that there are 3 negative signs and then an imaginary positive. So going back to the phase diagram, we're able to now put those signs into the phase diagram. So -1 is below 0, and we're able to see that that goes down. +1 is a negative also, so that also goes down. 901 is a positive, so that goes up. Now remember, 900 is our minimum, 10,000 is our maximum, so it makes sense that our population would want to rise to 10,000. And then 10,001 is down. So now that we've got our arrows on here, we can map it out. Now remember that these are asymptotes, so even though this is decreasing, it's not going to decrease exponentially like it will here, because there's an asymptote to stop it. So it's going to kind of curve like this, like an hourglass almost. And similarly here, but the opposite way. And this is still decreasing, so it's going to be a little more exponential, but kind of like a asymptote. So now we've got our phase diagram here. Now the question on WeBWorK for problem 13 is assuming, part 1 at least says, assuming that p is greater than or equal to 0, which makes sense because we cannot possibly have a negative population. It's asking us to find what values of p is the population increasing. So we see here through our phase diagram that it's only ever going to be increasing where p is equal to either 900 or 10,000. But we don't have brackets, we have just normal parentheses to indicate that it's not equal, or it's not going to be increasing at the value 900 or at the value 10,000, because those are asymptotes like you see up here. Now question number 2 is asking where, I'm going to make a little note just to say where it's increasing. It's asking where it's decreasing. Now we have a whole bunch of intervals. And originally when I was solving this problem, I disregarded the fact that the question is asking for values where p is greater than or equal to 0. So I actually added in from negative infinity to 0 here. But we don't have to do that because the problem clearly states that I couldn't read apparently. So we see that the problem is decreasing when p is between 0 and 900 and greater than 10,000. So to write that, we have to remember to use parentheses again because all these values are going to be equilibrium points. And then to say or between intervals, WeBWorK thankfully gives us this little capital U. I think one of the problems before it didn't actually make that point, so I was trying to figure out, am I using an and symbol on the computer? But if you were to just go a little bit farther into the WeBWorK problem, you would see that it uses this actual capital U letter. So then the second interval that's decreasing is going to be 10,000 to infinity. And, WeBWorK says you can just say INF for infinity, which also works.